Hi students, welcome to the next lecture of switching theory and logic design. So coming to in this class we will see majorly two topics. The first one, 3-level logic circuits, and second one, NAND NAND realization. So our main focus is NAND NAND realization. So first we will see 3-level logic circuit realization. So in the previous class we have seen different types of sum of minterms and product of max terms. So there we have only two levels. The first minterms. After minterms, we are adding those minterms. That is seems to be like as a, for example, f is equal to AB plus CD. AB plus CD. So AB is a minterm, CD is a minterm, and we are adding those two minterms, AB plus CD. So generally, most of the Boolean expressions we are realizing this type of sum of minterms or product of max terms. But if you have the given function like this, then how to represent this function? So see here, we have this function. Now we have to implement this function. This is also an example of see here. First one, A, B bar. So the first product term is A, B bar. Okay. Next product term, A bar, B. So this one is A bar, B. And next one, C plus D bar. Okay. So coming to here, I said that 3-level logic realization. So now we will draw this diagram, and then we will see how many levels will be available in the given this diagram or not. First see here, A, B bar, A, B bar. Next, A bar, B, A bar, B. So directly I am saying that this is A and this is B bar. Okay. So now I have drawn this diagram, and so see here, this one is A, B bar, this one is A bar, B. So two product terms we got, that is we got two min terms. It's not min term, it's nothing but a product term. So with using AND operation, A, B bar, B. So those two AND gates we have drawn here. Next, these two AND gates we are doing the OR operation. So here, for these two outputs, draw an OR gate, and this is the output of this whole term. So this is the output of this whole term. So this OR gate is sum of A, B bar plus A bar, B. So this is the first operation. So this is the level. And see here, you can do the AND gate operation, this A bar, B and A, B bar, these two AND gate operations we can do parallelly. There is no need of waiting. Why? Because A is available readily and B is available readily, A bar, B bar, those four signals available readily. These two functions we can do parallelly. Okay, if you want to do the sum operation, you need these two AND gate outputs. Okay, right. Next, so another function here we have C plus G bar, C plus D bar. So see here, when you are doing A, B bar operation, parallelly you can do C plus D bar operation also. C plus D bar, that is we have to use an OR gate here. So one signal is C and second one is D bar. One signal is C and second signal is D bar. Okay, you can represent here. You have to represent all signs with either bar representation or apostrophe representation. So see here, A, B bar, B and C, D bar. So these are the C, D bar. C, D bar, for the C, D bar we have to use an OR gate operation. This is the OR gate operation. Okay, right. So this is OR gate output and this sum of A, B bar plus A bar, B. So you have to multiply, that is you have to use a product term. So this is the product term. And this is the final output F. This is a given function F. So see here first, here we have one term C plus G bar and another term, that is A bar B plus A bar, A B bar plus A bar B. So this term and this term we have to product, that is we have to use AND operation. You have to combine these two expressions. So see here, this expression and this expression. So for your better understanding purpose, I rounded these two terms. This term you have to do the AND operation. So when you are doing this AND operation, you have to be ready with this operation. What is this operation? A B bar plus A bar B. For implementing this operation, we have drawn the logic here. This is the first term. So this is the first term and this is the first term. This is the first one, and this is the second one, and this is the second one. This is the second one. So first one, second one. So for first term, second term, you have to do the AND operation. You did the product operation. But getting this product, for example, if you want to do this operation, you have to be ready with this 1 and 2 operation. So if you want one operation in this first, you have to implement A B bar function, A bar B function. These two functions first you have to implement, and then you will get this operation. See here, if I have some time periods, So for example, first time period, I will do this A B bar operation and A bar B operation and C plus D bar operation. So in the first time period, I have to compute this one. In the second time period, I have to compute this one. This is the second level. So this is the first level gates. So this is the second level gates. After getting only, you can do the product operation. Without doing this operation, you can't do anything. So at a time, we can do some of the operation. So this is the first level. See here, this is the first level. And this is the second level, and this is the third level. So here you can write here. So this is the first level, and this is the second level, and this is the third level. Right? So first level and second level, third level. In the first level, you can compute this operation. If you want to do the product operation between these first and second terms, you have to compute this sum operation. That is the second level operation, and this is the third level operation. So today the total world is using different types of electronic gadgets, but each and every electronic gadget has two common parameters. The first one is less power utilization, and second one is very speed in operation. If you want to do with very fast this operation, first in the first level period we are doing this operation. If you want to do this one, you need OR gate of these two AND gates. So for that reason, this will require the second time period, and it will require third time period. First time period, second time period, third time period. Generally, we will explain this concept in the electronics integrated circuit level. We have 3 clock pulses: first clock pulse, second clock pulse, third clock pulse. So for computing this complete circuit, you need 3 clock pulses. Otherwise, within a simple language, you can say that in the first level, second level, third level. That is nothing but as 3-level logical operations. So this is an example of 3-level logical operation. It's very simple. Just we have taken an expression. For that expression, we have drawn the logic diagram. That logic diagram is representing with the 3 levels of this circuit. So these are the example of 3-level logic circuits. Next. So see the simplified diagram here. So this is a finally expression what we have drawn here. The first one A B bar, next A bar B, next C D bar. So this is OR gate operation. These two AND gates we have to make sum, and after making the sum, you have to product this operation and this operation. That is the first term A B bar plus A bar B, and the second term C plus D bar. You have to product these two operations. So this is a final function representation. Okay. Next, in the previous class we have seen logic gates realization using NAND gates and NOR gates. The same concept I am going to explain here. These are the basic fundamentals for converting any type of Boolean function with using NAND gates. In the last class only we said that when you are manufacturing some hardware, different types of logic gates will consume different types of power, and their AND gate has a separate circuit, OR gate has its separate circuit, and NOR gate has separate circuit. For each gate it has different types of circuits. So different types of circuits manufacturing on a single chip, it will get very complications. So for that reason, so on a single chip, same type of that means we are using only one type of gates, either using NAND gates or NOR gates. So on a single chip we are using only NAND gates. Whatever the function you want to implement, for all the functions you are using NAND gates. By using only single gate, you are implementing different types of functions. In the last class, if you want to implement an AND gate, how to use an AND gate, how many number of NAND gates you required for implementing the AND functionality, that is we have seen in the last class. The same concept we will see now, but using some diagrams. Diagrammatically we will see. For example, see here, this is the AND gate operation. You want to convert this AND gate into NAND gate. What you have to do is very simple thing. If you want to convert this AND gate into NAND gate, just place a bubble here. So just place a bubble here. Okay. So then this bubble, for example, here we will get some X signal or Y signal. So after placing this bubble, the signal is converted to Y bar. Okay. Previously it is Y. Now it is Y bar. Okay. So here again we have a bubble. So Y bar and one more bar. So Y double bar is equal to Y. So this bubble is nothing but as an inverter. In the previous classes also I said that for representing the inverter, bubble is also more than enough in some situations, not in the all situations. In some situations we are saying that the bubble is representing as the inverter. Remember, this is very important. So this bubble acting as an inverter. So see here, at the place of AND gate we have placed a bubble. So this is converted as a NAND gate. So but actually here the operation is AND gate. So extra we added one bubble. So for neutralizing that, I have added one more bubble here. So this is the neutralization process. Finally I will get the output Y. Okay. So next, coming to here in the third step, here I have used NAND gate, but I said that you have to use only NAND gates, but the bubble is representing NOT gate. How to replace this NOT gate by using NAND gate? So this is the procedure. So it is very simple thing for implementing the AND function. In the previous class, I have drawn the same diagram. So I explained the same diagram now. So this is the implementation of AND gate by using NAND gates. So this is the first NAND gate and this is the second NAND gate. This bubble also I am representing with using NAND gate. I am not taking any NOT gate, AND gate, OR gate here. Only I am taking NAND gates only. In the same way, for representing the OR gate also, see here. So this is the logic symbol of NAND gate and this is the logic operation of the NAND gate. If both inputs are 1, 1, then only the output is 0. In the remaining situation, all the outputs are 1. So this is the NAND gate operation. Next, coming to that OR gate operation, we have seen how to represent the AND gate by using NAND gates. Now our concept is OR gate using NAND gates. How to represent OR gate by using NAND gates. So we know that OR functionality. What is the OR functionality? Input AB and Y is equal to A plus B. This is the OR gate functionality. OR gate functionality. Okay, so coming to here, what is OR operation? If any one of the input is equal to 1, automatically the output is equal to 1. If both inputs are 0, output is 0. This is the OR gate operation. Okay, now you want to implement this function by using NAND gates. So for that reason, I am doing a small modification. So the OR gate is available. Now I want to give the inputs A bar, B bar to this OR gate, right? Actually I am giving the input AB only here, but I want to give the complemented inputs to this OR gate. Okay, so that generally we are placing the inverters before to the OR gate. So it's very simple thing. I am placing the inverters for AB before the OR gate. That is generally called as bubbled OR gate. So this is an example of bubbled OR gate. See here. So OR gate is there. So here I placed a bubble and here I placed a bubble. So this bubble is representing inverter. So for that reason, for this OR gate, I am giving the B bar input, A bar input, B bar input and A bar input. So these are the two inverters. So this type of gates are called bubbled OR gates. This type of gates are called bubbled OR gates. So this bubbled OR gates, see here. So output y is equal to, here a plus b operation is there previously. Now this is bubbled, that is a bar b bar signals we are giving. That is a bar plus b bar, a bar plus b bar. So see here, ab is equal to 0 0 0 1 1 0 1 1. But I need the operation y is equal to a bar b bar. So ab, you have to understood this one, a bar b bar. You have to convert this first, a to a bar. Then it makes 1 1 1 0. Then it is 0 1, next 0 0. So this is the inputs actually for a bar b bar. Then coming to the outputs. So these are the outputs. See here, y is equal to a bar plus b bar. Okay. If inputs a is equal to 0, b is equal to 0, a bar is equal to 1, b bar is equal to 1. 1 plus 1, that is equal to 1. So this is the first one, y is equal to a bar plus b bar. Next coming to here second situation, 0 1. Then here 1 0. 1 plus 0, that is equal to, what is the answer? 1 plus 0, that is equal to 1. So here this is 1, not 0. Not 0. Next coming to here. So here also 1. So see here 1 1 1 0 0 1 0 0. Last case we have 0 0. When you are considering these inputs are a bar b bar. Actually I have written ab, but here for this OR gate the inputs are a bar b bar. So consider here a bar b bar is there, but actually here we have written 0 0 0 1 1 0 1 1. You have to write down the reverse operation, that is 1 1 1 0 0 1 0 0. If any one of the input is equal to 1, OR gate output is equal to 1. So here in the last place, in this 1 1 place I am giving, in this 1 1 place I am giving 0 0 input, this situation. In the remaining combination this is 1 1, it's not 0 0. If it is a bar b bar, here I have written ab only, but I am considering here a bar b bar is there. So then answer is 1110. Then answer is 1110. Right? So this is the 0 0. For example, if it is a bar b bar, it is 0 0. 0 plus 0 0. And in the remaining combination all the outputs are 1. So this is the bubbled OR gate operation. Bubbled OR gate operation. Remember, this is the bubbled OR gate operation. So see here now, this is the NAND gate operation. This is the bubbled OR gate operation. These two are same or not? See here, it's very simple thing. NAND gate output 1110, bubbled OR gate output 1110. Both are same. So finally, what I am saying here, bubbled OR is equal to NAND gate. So see here, NAND gate is equal to bubbled OR gate. So if you have bubbled OR gate, just remove that bubbled OR gate and replace with NAND gate. Both are same. Both are same. So here I am giving a conclusion. Bubbled OR is equal to, it's very simple thing. Bubbled OR is equal to NAND gate. Okay. Next, coming to here. So here we have OR gate. This OR gate we are representing with bubbled OR gate. Bubbled OR gate. And the inputs are, now the inputs are a bar, b bar. Inputs are a bar, b bar. Next coming here, that bubbled OR gate we are representing with NAND gate. But here the inputs are a bar, b bar. For the OR gate, the inputs are ab. But bubbled OR gate, inputs are a bar, b bar. Remember, now for normal OR gate, inputs are a, b. For bubbled OR gate, we have the inputs are a bar, b bar. And this bubbled OR gate we are replacing with the NAND gate. Now the inputs are a bar, b bar. Right? If you want to draw, you can draw this signal. So a bar, b bar is there. Right? A bar we are representing with NOT gate, and b bar we are representing with NOT gate, like that. So this is the A signal, this is the B signal, and this is the A bar signal, and this is the B bar signal. Here we have NAND gate operation. This is Y. This is Y. Right? Now with the help of NAND gates, remove this NOT gates and replace here NAND gate. So here you have to replace NAND gate. Here you have to replace NAND gate. Two NAND gates are available. So that finally, whatever the OR gate we have seen in the previous class, the same circuit is available. So now I am replacing the NOT gate with using NAND gates. So So this is the expression we have seen in the previous class. A signal, B signal. Here for the first NAND gate, two inputs are A, and here the second NAND gate, two inputs are B. So this is A bar, this is B bar, and the third NAND gate, it converts this operation into A plus B. So A bar dot B bar whole bar. This is a NAND gate output. If you simplify that one, you will get A plus B operation. So this is the NOR gate representation. So if any OR gate available in the given circuit, if you want to convert that circuit into NAND gate, just replace this OR gate with a bubbled OR gate, and if input here you have to put A bar, B bar input. That is, you have to add two more NOT gates here. So like this, we have to convert OR gate into NAND gate, OR gate into NAND gate. Now we will see one example here. Multi-level NAND circuits we have to realize. So see here, A of CD, A of CD plus B into BC bar. So see here, what are the functions available here? B, C bar is available. Okay, B signal, C bar signal, and I am using a NAND gate here. So sorry here, BC bar, that is an NAND gate. First, draw this circuit as it is. First, draw the given circuit as it is. So here, first one, A of CD plus B. First to draw CD signals. So this is the C and this is the D signal, and you have to add this signal, this is CD with B. So this is the CD operation, and this is the B. So CD plus B operation. You have to multiply the CD plus B into A. So this is the A. Right? So this is the AND gate. Next, BC bar. You have to add this term, you have to do OR gate operation with BC bar. BC bar. CD. This is CD plus B. So see here, C, D. Next, this is B and this is A. So this is the final product. Next, B, C bar. So normal logic diagram I have drawn here. Right? So this is the normal logic diagram I have drawn. This is the first step. This is the first step. So what is the question? Multi-level NAND gate circuit. So this example, whatever the circuit they are given, you have to convert this logic into the NAND gates. That means finally you have to draw only NAND gates here. Finally, in your circuit, only NAND gates must be available. No other gates available. No other gates availability here restricted. So okay, finally we have to represent all the components with NAND gates. Okay, so the complete function. Previously, AND gate, OR gate, XOR gate, XNOR gate, these functions we have replaced with NAND gates. Now each and every the NAND gates. Okay, so what I said previously, here wherever the AND gate is available, just to replace this AND gate with choosing NAND gate. So see here, so the same circuit, this is the first step. Now coming to the second step, CD signal, CD here available, and AND gate is available. So AND, in the place of AND gate I am placing a bubble. So this is converted as a NAND gate, and we need this AND gate we have to replace with NAND gate, and we have to add one more bubble. Then bubble, two bubbles are cancelled and you will get the original signal. So here I have placed one more bubble here, one more bubble. This bubble cancels, and again you will get the AND gate functionality only. Okay, this bubble is nothing but as input for this OR gate. Okay. So this is the OR gate I have drawn here, and here B signal is there. B signal is there. So I said previously, bubbled OR we can replace with using NAND gates. So for that reason, one signal is bubble with the neutralizing this NAND gate with AND gate. I have placed one bubble, and B signal is there. For B signal also I am placed a signal. Now here the input is B bar. Here CD signal as it is there. So B signal is I have changed it to B bar. Okay. So this here it is B bar. Then this bubble makes B bars to B. B bar and inverter B double bar, then it becomes to B. Okay, next this OR gate I'm placing here. Otherwise you can draw like this also. You erase this B bar, replace with B, and so this is a B signal, and you draw an inverter here and connect like this. Okay, so you have an inverter here, and this inverter, this bubble, both are cancelled, and you will give the input B directly to this OR gate. Okay, so bubbled OR gate is available. Next, here AND gate is visible, so replace this AND gate with a bubble, and one more input here, it is A. Next, for neutralizing this bubble, you have to place one more bubble here. Two bubbles, bubble cancel, and you will get the original signal. So here we have an OR gate. So this bubble we are placed at the in front of the OR gate. Now see here, B C bar signals also. B signal, C bar signal, C bar and B. Here we have an AND gate. AND gate you have to replace with NAND gate. Put a bubble and put one more bubble here. One more bubble here. So now this is the output of F. So see here, there is no changes have done here. AND is there. In this in between this AND gate and this OR gate, I have placed two bubbles. So this is the first bubble and this is the second bubble. Bubble cancels, directly the AND gate output goes to the OR gate. So see here, I am not doing any new thing. So double bar cancels to, for example, A bar whole bar is equal to A. Okay, right? For example, here B C bar signal is there generally. So I placed a bubble. Now B C bar whole bar. So after placing this one, B C bar whole bar guide. So again here we have one more bubble. So B C bar whole bar and one more whole bar. Two bars cancels finally. B C bar is the input for this one. B C bar is the input for the OR gate. So just I replaced the AND gate with using NAND gate and I added one more bubble here for neutralization purpose, for getting the same signal purpose. I have placed two bubbles. So two bubbles we can cancel. Here also we can cancel two bubbles. Like this we replaced the signal. And so in this circuit we know that this is the NAND gate. I said that all the gates should be available with using NAND gates only. So the first signal CD input, that is the NAND gate we placed already. Bubbled OR gate we can replace with using NAND gate here, and this NOT gate we can write with using NAND gate like this, right? A and sorry CD, this is CD. So this is C and this is D. And this is B and next A, right? Here one more NAND gate. This is connected to the A, this one. Next this NAND gate. This NAND gate I have drawn here. Now bubbled OR, this bubbled OR we are replacing with the NAND gate. Okay, this bubbled OR we are replacing with the NAND gate. And this is already we have placed with NAND gate. So here finally I have only NAND gates. This is the third step. This is the third step. Okay, it's very simple thing. Here the internal key point is A double bar is equal to A. Okay, so this AND gate I replaced it with NAND gate. Actually I need AND gate operation only. Extra I got an inverter operation. For eliminating that inverter operation, I placed one more bubble here. A double bar is equal to A. So for that reason I placed two inverters here. So we know that bubbled OR is equal to NAND gate. Bubbled OR is equal to NAND gate. We have seen in the previous slide. So for that reason here also I have placed one more bubble. For getting this one as B, so I have placed one more NAND gate here. So these two are the NAND gates. So finally I have given the B signal to this OR gate. So in this way I did the second step. In the third step, the bubbled ORs I have replaced with NAND gates. Already NAND gates have some of the NAND gates available in this circuit. This bubbled OR I replaced with NAND gates, and this NOT gate also I replaced with the NAND gates. So the finally here is the circuit, the same function which we have seen here, the same function we implemented by using NAND gates. The same function we implemented by using NAND gates. So this is the procedure how to implement any type of given Boolean function by using NAND gates. And it has multi levels. First level, second level, third level, fourth level. So we have 4 levels in this function. Totally, we have implemented this function by using 4 level NAND gates. So for that reason, this topic named as multi-level NAND gate circuit. This topic is named as multi-level NAND gate circuit. It is very simple concept. Okay, so you have to note down this one. And next, coming to that one, this is the finalized circuit. So see here, so this is the example of that circuit. So see here, in the first step we have drawn the normal and or logic diagram, and the second one by using NAND gates we implement for implementing to the NAND gates. This is the second step. So this AND gate we are placed with the NAND gates, and one bubble is there, and this bubbled OR we are replacing with the NAND gates. So this is the second step, and third step we have already drawn. Okay, so this is the procedure. Next, so example 2. So this example 2 you have to make practice a b bar plus a bar b into c plus d bar. So this is also you have to implement with using NAND gate. So the question is, implement the given following function with using NAND NAND logic. In the exam hall, in the exam paper, the question is asked like this. You have to implement the given function by using NAND NAND logic. Otherwise, you have to implement the given function by using NOR NOR logic. So you have to do this one as a practice. So you have to complete this exercise. So this is a solution for this given problem. So I have given the first step, second step, third step, just to replace this bubbled OR gates with the NAND gates. So that is the final step. Next, multi-level NOR circuit. Now, how we did the NAND gate, like that also you have to implement NOR also. What you have to do, so if the OR gate is given, just to replace this OR gate by using a NOR gate and place one more bubble also here. So this is the final output Y, and this is the A, and this is B, and this is the A, this is B. Right? For OR gates you have to replace with the NOR gate, and you add one more bubble here also. I drawn the big bubble, so don't bother about that. Draw a small bubble. Next, okay. Next, coming to that bubbled AND gate. Previously we have taken bubbled OR gate. Now take this bubbled AND gate. What is the function of this one? See here, A, B, and this is the Y. Y is equal to what is the value? So A changes to first inversion operation we are doing. Then only we are doing the AND operation. Okay, first inversion operation, then AND operation. A is changed to A bar, B is changed to B bar. In between A bar, B bar, we are doing AND operation. This is the A bar dot B bar. So just think this one. So how you can write? So place 2 bars in this function, A bar dot B bar. Okay, 2 bars I have written, that is 2 double bars. So this bar get cancelled. This is nothing but as A bar dot B bar. Like A double bar is equal to A, otherwise X double bar is equal to X, like that. So 1 bar keep it here and apply this bar to this function. Okay, so then this function A bar changes to A, dot changes to plus, and B bar changes to B, and whole bar, 1 bar is available. This bar we have applied. So finally, what you got the function finally, Y is equal to A plus B whole bar. Y is equal to A plus B whole bar. So that is nothing but as NOR gate. So bubbled AND is nothing but as NOR gate. Bubbled AND is nothing but as NOR gate. So see here. So inverter we are implementing with using single NOR gate, we know that, and OR gate if you want to implement, here you are using a NOR gate. In the place of NOT gate also we can use NOR gates, and AND gate functionality. In the place of NOT gate you place NOR gate, like what we did in the NAND gate place. You have to implement this one. So here I have given the circuits. In the place of you have to put NOR gate and draw the logic. The same logic you have to draw again. Next, so see here. So this is the OR and invert operation. Generally we are calling this is NOR gate operation. So see here we have bubbles and AND gate is there. So this is called bubbled AND gate operation. This is called bubbled AND gate operation. So this is OR invert. This is called invert OR, invert AND. This is called bubbled OR gate. Bubbled OR gate is equal to NOR gate operation. Next, coming to example here, the example 1, right? The circuit is very simple. A plus B, A plus B. So this is the A plus B. C plus D, C plus D. So this is a C plus D. A, B, C, D. Okay, you have to multiply all this one. E signal is also available. So these 3 signals you have to multiply. That is, you have to use an product operation, that is a AND gate operation. So this is the given circuit. This is a given circuit logic diagram. You have to replace this complete circuit with using NOR logic. We have to implement only NOR gate and NOR gate logic. In the first OR gate place a NOR gate. So OR gate I am converted as NOR gate. In second also I have placing here NOR gate. And the OR gate I have placed as, so here OR gate 1, OR gate 2. OR gate 1 I am replacing with NOR gate, and I place a NOR gate. So here the bubble, both bubbles are going to cancel. I will get the same function. Now these are the inputs for this AND gate. So this is the AND gate. This is the third one. This is the third one. And E signal is there. So see here, this is A, B, C, D. E signal is there. I am placing a NOT gate here. And this NOT gate I connected here. Here also I placed a bubble. So there finally this is the output F. This is the output F. Okay. So this bubbled AND we can replace with NOR gate. So these NOR gates are directly available. This NOT gate also we can implement by using a NOR gate. Okay. So finally this is the circuit. This is the circuit. So 2 NOR gates and bubbled AND gate is available. Now convert this function into, right. So the final step, coming to the final end step. So this is the first NOR gate I have completed. This is the second NOR gate completed. In the place of inverter, I am placing a NOR gate. This is also completed. And bubbled and I am replacing with a NOR gate. 3 input NOR gate. Right? So this is AB, this is CD, and this is C. So this is the third step. First step, second step, third step. In 3 steps you can convert any type of logic into NAND NAND or NOR logic. So this is a very simplification process. So diagrammatically I am converting any given Boolean function into the NAND NAND or NOR logic. This is the example of NOR logic. Okay, one more example is there. So this is the final solution. And coming to the next example. So A B bar plus A bar B into C plus D bar. So this is a solution. You have to do this practice. Okay, thank you.
Good morning, students. Today we will discuss duality principle in the switching theory and logic design subject. Okay, coming to duality principle. First, coming to the definition of duality principle. This duality theorem states that the dual of the Boolean function is obtained by interchanging the logical AND operation with logical OR operation and zeros with ones. For every Boolean function, there will be a corresponding we have conversions. Okay. So coming to here, this is the theorem statement. Coming to justification of this theorem statement. So it is almost all similar to the De Morgan's property. Coming to the De Morgan's property, when you are applying the De Morgan's property, the complement, when you are applying the complement for a given function, the A changes to A bar, B changes to B bar, 0 changes to 1, 1 changes to 0, and addition of plus operation changes to AND operation, that is dot operation. Otherwise, the AND operation changes to OR operation. So these are the very important parameters. So coming to here, 0 changes to 1. Next, 1 changes to 0. Next, AND operation changes to OR operation. Okay, next OR operation changes to AND. Next, A changes to A bar changes to A. So in this way, we have different types of conversions in the De Morgan's property. So coming to here, the duality property. Coming to here, the duality property. In this duality property, here we are not doing these operations. Here we are not doing these operations. So in the duality operation, we are doing AND to R to AND, and 0 to 1, 1 to 0. That we will see now. That we will see now. Right. So coming to here, for explaining this duality property, now I am taking the help of Boolean postulates and theorems. What we have learned in the Boolean theorems and postulates property, there we have seen these functions. Those functions are, so these are the functions. Coming to here, these are the postulates 2a and 2b, postulate 5a, 5b, theorem 1a, 1b, and theorem 2a, 2b, theorem 3a, 3b, postulate 3a. Like that, we have different types of theorems and properties. Here we have a small magic in between a and b. In the postulate 2a and 2b, we have a small relation. See here, I said that the plus changes to 0, the plus changes to and changes to plus. Next, 0 changes to 1, 1 changes to 0. Here, but the x does not change here, the variable does not change. For example, see here, coming to postulate 2a, x plus 0 is equal to x. So this is the postulate 2a. This is the postulate 2a. Coming to the postulate 2b, x does not changes here. There is no change in there is no change for the x. There is no change in the variable. The plus operation changes to dot. The plus operation changes to dot. 0 operation changes to 1. 0 is changes to 1 and equal to the x. There is no change. So this is the property of 2a. This is a property of 2b, postulate 2a, 2b. So this is a relation between 2a to b. So the variable, there is no change in that variable. X may be before the duality, after the duality, there is no change in the x variable. The plus operation changes to dot, dot operation changes to plus. Next, 0 changes to 1, 1 changes to 0. So these are the changes we have to observe in this duality operation. Next, coming to the postulate 5a. Coming to the postulate 5a, x plus x bar is equal to 1. That is, x plus x bar is equal to 1. X plus x bar is equal to 1. So there is no change for the variables. So write down x as it is. Okay. Plus you have to change. Plus changes to dot. X bar only. Next, equal to 1 changes to 0. This is the postulate 5a. This is the postulate 5b. This is the postulate 5b. So see that what we have mentioned here in the postulate 5a, that is that the same thing we have written here. So the x does not changes before duality, after duality, but the change, but there you can observe the change for the plus dot operation, for the zeros and 1 operation. So I think this is very clear to you. So here in the duality operation, the change you can observe at the AND operation, OR operation, logic 0 operation, logic 1 operation. The duality principle we are not applying for for the given variables. So this is about the duality operation. Now coming to the next theorem 1a, 1b. So everything you have to see here. Okay, except the theorem 5a, so you can check the remaining all the things. You can observe the change. Even in the theorem 5a also you can observe the behavior, but there is a small change for that, so you don't bother about that. Except theorem 5a, check all the remaining postulates and theorems. You can check here. So there is no problem at all. All the functions are satisfying the duality principles. All the functions are satisfying the duality principle. Okay, right. Now here we will see a small problem, that is, so this is the problem we gathered from the digital design by Maurice Meno textbook at the second chapter. At the second chapter end, we have nearly 50 problems. In that 50 problems, the 2.24, that is 24th problem, 2.24, show that the dual of XOR is equal to its complement. Here the problem is show that the dual of the XOR gate is equal to its complement. We know that what is the XOR function? A XOR, we are representing the XOR symbol in this way, A XOR B. So what is the complement of this one? The complement of this one is A XOR B whole bar. This is the complement of the function. Okay, right. This one you can represent in this way also. So the complement of the XOR function generally we are representing with XOR function. So the complement of this XOR function, it is nothing but as A XOR function. We know that what is A exclusive or B? A bar B plus A B bar. A bar B plus A B bar. Coming to what is the XOR function? A B plus A bar B bar. So this is the XOR function. It's very simple thing. So this is the XOR function. This is the XOR function. So what is the problem statement? In this problem statement, show that the duality of the XOR gate is equal to its complement, XOR complement. So here the question is, you have to find the dual for this function. Here the given function is A exclusive B, that is A bar B plus A B bar. For this function, if you find the duality, then you will get the answer is complement of XOR operation. It is very simple operation. Now we will see. So that explanation I have already written here. So see here, now I have explained this operation with AB, but in this theorem I have mentioned in these steps with X, Y. So here the X operation, X exclusive Y, X XOR Y. See here, X exclusive R Y, right, is equal to X bar Y plus XY bar. So this is the XOR operation. Here the input variables are X and Y, right. So coming to here, what is the complement of this one? X exclusive R Y whole bar, that is equal to XY plus X bar Y bar. That we can represent with using the max term also. This is the max term explanation for XOR operation. X plus Y bar, X plus Y bar into X bar plus Y. So this is the operation. You can multiply this one. So X into X bar plus XY plus Y bar into X bar plus Y bar Y. Okay, after simplifying this expression, you will get xy plus x bar y bar. So this is a XOR function. The first one is XOR function and second one is XOR function. Next, coming to the duality of x bar y plus xy bar. So here the given function is x exclusive or y, that we have represented with dual of x bar y plus xy bar, right? So in this function you can represent in this way. Okay, x bar y plus x plus y bar. So this is the function representation by using which property? By using which property? That is distributive property. By the distributive property. Okay, x bar y plus x plus y bar. You can write in this way. Okay, whatever it will be here the function, you simplify that function. Okay, now we will see that function. Okay, so duality, that we will see clearly. Otherwise, see here. So this is the given function. Okay, this is the given function. So this is the given function. So in this given function, x bar y plus xy bar. Okay, what is the duality operation? X bar does not changes, y does not change, x does not change, y bar does not change, because of those are the variables. Here the AND operation or operation only changes to the second step. So coming to this second step, in the first step, x bar dot y. So x bar dot y, the dot changes to plus. So here the dot changes to plus operation, that is x bar plus y, x bar plus y. Next, coming to here, the plus operation changes to dot. So see here, in between these two we have the dot operation. Next, x y bar. So see here we have x y bar operation. The x y bar operation changes to x plus y bar. Okay, so in between x y bar we have dot operation. So when you are applying the duality operation, the dot changes to plus, the dot changes to plus operation. So this is the dual operation. Next, coming to here, this is the final function. This is the the output function of the dual form. This is the dual of x. This is the dual of XR. Okay, this is the dual of XR. But we have to prove this is nothing but as complement of XR. We have to prove this one is complement of XR. Coming to here, the next function x bar, you multiply this one. So this is seems to be like as a plus b into c plus d. Multiply this one. That is x bar into x. So this is the first function, x bar into x, x bar into x. Okay. Next, coming to that, x bar into y bar. So x bar into y bar, this is the second term. X bar into y bar, this is second term. Next term, xy, this is the xy. So here the y into x, that yx is equal to xy. So anyone we can write by using commutative property. Next, y into y bar. Next, y into y bar. Y into y bar. So this is the property. Okay, so here the x bar goes to cancel, the x bar goes to cancel. Next, the y bar goes to cancel. So the next y bar goes to cancel. The remaining terms are xy plus xy bar. So the remaining terms xy plus xy bar. This one and this one. So xy plus x bar y bar. Next, coming to here, the simplification. So see here, this is the function is equal to x naught function. The x naught function finally we are representing like this. The x naught function finally we are representing like that. That is x exclusive or y whole bar. So this is the proof of the dual of the function XR get. So here there is a final conclusion. The XR function duality principle, if you found the XR function duality function, if you found, the final output is nothing but as the complement of the final output is nothing but as the complement of XR function. So this is the proof. This question in the previous question papers, they asked nearly I think 5 marks, that is 4 marks question. So previously 2 marks questions, 3 marks questions are there. In the big questions, that is 2A, 2B. So 8 marks is there. In that 8 marks, the 4 marks bit is this one. The 4 marks bit is this question. That is show that the dual of the XR function is equal to its complement. Okay, right. Now, next we will see one example. I think we have seen lot of problems in the previous class, but they are not enough for this. They are not enough. Though for that, from the previous question papers, I have taken a problem. That problem we will see now. So here the next problem is simplify. Next problem is simplify the following expressions. Simplify the following Boolean function to a minimum number of literals. So here the problem is very simple. Simplify the following Boolean function to a minimum number of literals. So what is meant by literals? What is meant by literals? So previously we have seen variables. Those are the input variables. Okay. So here, for example, okay, in this function, how many input variables are there? So previously we saw about this problem. In this function, how many input variables are there? Yes, we know that 3 input variables. What are they? A, B, C. 3 input variables are there. Now coming to, in the same function, how many literals are available? How many literals are available? So the answer is 6 literals are available. 6 literals are available. So A is 1 literal, A bar is another literal, B is 1 literal, B bar is another literal, C is 1 more literal, and C bar is the 1 more literal. So in this function we have totally how many literals? Total 6 literals are there. So A is we are considering as different, A bar is we are considering as different. So each one is we are representing literals. Actually here totally 9 representations we did in this expression, but A repeated 2 times. So A is 1 literal. How many times if you want to write, you can write. But here we are considering only A is 1 literal and B is 1 literal, C is 1 literal. Like this we are considering the literals concept, right? So here what the problem given the description is, simplify the following Boolean function to a minimum number of literals. That is the problem. And given the function is equal to f is equal to abc is equal to f of abc is equal to sigma 1 4 5 6 7. Okay, and this question is given in the previous question paper, November 2019 regular question paper in set number 3. Question number is 3a. Question number is 3a. So this is the problem. Now first we have to minimize this function. Okay, coming to here, here the question is, it is nothing but as f of a b c is equal to, you can write this question like this. So sigma small m of 1 4 5 6 7. So this is the problem. Okay, so here in this problem m is not defined. Okay, sigma only defined. So but I have represented sigma m. So it's not a big problem. Both are same. This one and this one both are same only. So m is nothing but as this is a min term. What is the min term value? We know that the min term value m1 is equal to 0 0 1. That is equal to a bar b bar c. So this is the first min term. This is the first min term. Next, coming to the m4. M4 is equal to 100. That is a b bar c bar. A b bar c bar. This is the m4 min term. This is the m4 min term. Next, m5, m6, m7. Like that, we have to write the min terms. m5 is equal to 101. That is equal to a b bar c. So this is the m5 min term. This is the m5 min term. Next, coming to that m6. This is 110 and m7 is equal to 111. So coming to here, this is a b c bar. This is a b c. So these are our min terms. These are our min terms. So this function is nothing but as, you can write this function that is equal to m1 plus m4 plus m5 plus m6 plus m7. m1 plus m4 plus m5 plus m6 plus m7. Okay, this function, what is meant by m1? m1 is nothing but as a bar b bar c. m1 is nothing but as a bar b bar c. a bar b bar c. Plus m4 100, that is a b bar c bar, plus and m5 function 101, that is a b bar c, plus m6 110, that is a b c bar, plus m7 is nothing but as 111, that is a b c. So this is the given function. This is nothing but as finally our function f is equal to a bar b bar c. Okay, like that we have to write. Okay, here don't write this one. Why? Because maybe a chance of getting confusing. Right. Okay, so this is the given function. So now we have written the given function in the form of sum of min terms. This is called sum of min terms. So this is the given function. Is it clear? So here the given function is sigma small m of 1 comma 4 comma 5 comma 6 comma 7. That is, we have written m1 plus m4 plus m5 plus m6 plus m7. m1 is nothing but as 0 0 1. That is, we are representing with input variables a bar b bar c. Like that we have written the function. So here the question, here we have written the given f is equal to sigma of 1 4 5 6 7 with sum of min terms only. But the question is simplified. But the question is simplification. Simplification is required. So take the common from these parameters. Okay, from these two variables, what we can take common? Here a bar c, is there any other way, other place? No. So next, see here. From these two terms, we can take common ab. From these two terms, we can take common ab. Okay, next, from these two terms, we can take common a b bar. So first write down a bar b bar c, plus from these two terms you can take the common a b bar and c plus c bar. So this is the, after taking the common a b bar, this is the remaining value, plus next one you can take common from this two is ab. The remaining value is c plus c bar. So this is the function. This is the function. Next, so after simplifying this, we know that c plus c bar is equal to 1 into anything. So this one goes to cancel, and next this one goes to also cancel. So c plus c bar goes to cancel. So the final remaining function is okay. Function is a bar b bar c plus a bar b bar c plus next what is the final value? A b bar plus ab. Okay, now is there any further minimizations here? Is there any further minimizations? See here, is there any further minimizations? Right, you can take the copy. So b bar you can take common from this too. Right, so b bar take common. Next, a plus a bar c, a plus a bar c plus ab. Right, so next we can write a plus a bar c. Okay, right, over. Next, so b bar. So this seems to be like as x plus yz. This seems to be like as x plus yz from the distributive property. Right. So from the distributive property, here I am writing x plus yz is equal to x plus y into x plus z. So here I am writing a plus a bar into a plus c plus ab. Here I got a plus a bar. I am making this one as cancel. A plus a bar is equal to 1 into anything, that one. So finally b bar into a plus c plus ab. So this is the function. This is the finalized function. Okay, right. So this is the simplified function. You can write this function in this way also. You can write this function in this way also. That is equal to a b bar plus b bar c plus ab. Is there any further simplifications? Yes, we can take the common. We can take common from this a plus c, right, a b bar plus b bar c plus ab. Okay, so from this anything common, right, a you can take common. A, after taking common a, b plus b bar plus b bar c. So after taking simplification, this one goes to cancel. Finally a plus b bar c. So this is the finalized answer. This is the final answer. A plus b bar c, a plus b bar c. This is the finalized simplified expression. This is a finalized simplified expression for the given problem. So for this problem, you can represent first b bar c. Here I have placed a NOT gate. So this is the b input and c input. For this two, I have used this AND gate. Next, a signal. So this is the logic diagram, the final function f. So here f is equal to a plus b bar c. So this is the finalized function. This is our finalized function. This is the simplification process of for a given Boolean expression. And this question is from our previous question papers. Okay, right. In the next class, we will see some more problems. Regarding this simplification process, and maybe the next class we will start the second unit introduction. In the next class, we will see the second unit introduction. Okay, thank you.